So this video introduces basic antiderivatives. Now, to do so, notice that with the change in our environment, we notice the change. To motivate antiderivatives, we often notice the change in our environment as we interact with it. For this reason, it's natural to express the rate of change in terms of an equation. That rate of change, though, requires a derivative. So, as an example, if you want to find the velocity of an object starting at rest and undergoing a constant acceleration of 2 feet per second squared, that means the acceleration, being the derivative velocity, is 2. So then we might wonder, then what's the velocity function? I want to undo the derivative. To do so, you can guess that v of t could be 2t. That might be right. After all, this derivative is 2. But there are other answers. It could be also 2t plus 3 or 2t plus 5. Now, out of all these choices, only one of them gives you, though, that the velocity of 0 would be 0. So you'd be inclined to think that this is the answer. Now, this is dangerous, though, because there might be some other function out there whose derivative is always 2, and when you evaluate the function, you get 0. Maybe there's something else. After all, I'm just guessing. I'm not arguing anything. We need some way to systematically undo the derivative. Well, in order to find the antiderivative rule, we need a way to undo derivatives. That requires inverses. But differentiation doesn't have a true inverse. But we do have a result that we proved before because of the mean value theorem, that if two functions have the same derivative on some open interval, then they don't have to be equal, but if they're not equal, they're only off by a constant on that interval. So, as a definition, we will say that capital F of x is an antiderivative of little f of x on some kind of open interval if the derivative of the capital function, the antiderivative, is the original function. So the derivative of the antiderivative cancel, giving you the original function back. And that's true for every single x in the interval. We'll then notice that if you have any antiderivative and any other antiderivative of the same function, because of the previous theorem, they'd have to be off by a constant. So we'll denote the family of antiderivatives by this symbol. That would then be the integral of f of x dx, and it gives you all the functions whose derivative would then be f of x. All these functions would then be off by some constant. So as an example, the antiderivative of 2x dx is x squared, because that's one function whose derivative is 2x, and all the other antiderivatives must be 2x squared plus some constant. So as I said, the antiderivatives create a family of curves that differ only by a constant. That constant is given a name. It's called the constant of integration. Now the inside of an integral is called the integrand. This symbol looks like a big S. That's the integral symbol. And the dx is the integration with respect to what? So in this case, it's with respect to x. It tells you what derivative you are undoing. So here I was undoing a derivative in terms of x. Now, antiderivatives are just a way to undo derivatives. So you should expect that many of the derivative rules, there's a corresponding integration rule. So if you take the derivative of k times x, you just get k. So that means the antiderivative of a constant, dx, would just be the constant times x plus an unknown constant of integration. You know that if you take the derivative of this side, as long as n is not -1, that derivative would be x to the n. So the antiderivative of x to the n dx would then be this function plus a constant of integration. If n is -1, you'd have the antiderivative of x to the -1. And that would be the log rule. It's the antiderivative of 1 over x. If you take the antiderivative of a constant times a function, the constant just comes out. And if you take the antiderivative of a sum of functions, it becomes a sum of antiderivatives. And those two follow directly from the corresponding rules for derivatives, that the derivative of a constant multiple is a constant multiple of a derivative, and a derivative of a sum is a sum of derivatives. Integration follows a fairly straightforward path. It's just the first step, the rewriting stage. It requires sometimes a little bit of experience and quite a bit of algebraic manipulation. But in general, you take the integrand and you rewrite it. The purpose being to rewrite it into a sum or difference of things that you recognize. You then integrate all the functions you recognize, and at the end, you simplify the answer. The goal here being almost always we don't set antiderivatives equal to 0. Almost always we evaluate them. So pretty much don't leave negative exponents is the only rule you really should follow. In order to find an antiderivative, you usually have to be fairly strong in your derivative rules so you can identify what you're undoing. For example, if I were to find what is the derivative of the inverse sine of x divided by a, that would then give me, it would be 1 over the square root of 1 minus x over a squared, and I would multiply that by the derivative of x over a, which is 1 over a. But if I simplify that, that's 1 over the square root of 1 minus x squared over a squared times 1 over, but don't write a. Let's assume a is positive right now. I can then write that as the square root of a squared. That means that I could then combine the square roots and get the square root of a squared minus x squared. So that's the derivative of the inverse sine of x over a. Because of that, I can then use the same derivative in reverse to get, this is 4 times the antiderivative of 1 over the square root of 25 minus x squared dx. I can then identify the derivative rule that I know, it's just where a is 5, to get that this is 4 times the inverse sine of x over 5 plus an unknown constant. And that's the antiderivative of 4 over the square root of 25 minus x squared. Now, I teach my students a certain way to go about doing integration. This is not right or wrong. This is not found in books. This is really just me. So I use the acronym SAPFU, in order to remind students what to do in what order. That does not mean you have to go by this order. Many times I know exactly what needs to be done, and I just skip to the corresponding step. And with practice, you'll do the same thing. So the S stands for think simple. Your goal is to rewrite your integrand to recognize it as something you know how to do already. So you can use your vast experience with integration after you integrate for a while to go, oh, I know how to do that, and just skip all these steps and go right to the end. So can you simplify the integrand? That's the first question. If you can, do so. If you can't, then don't worry. Do you recognize it as something you've memorized or done? If so, then use that formula or use that technique. If you don't recognize it, then we start trying to make it look simpler. So is it currently a sum or difference? If it is currently, if the integrand is currently a sum or difference, you might want to break the integral up to many pieces and then consider each smaller integration, as they'll be simpler. Now, that often doesn't get us anywhere. So the next step is to rewrite, the goal being, can you turn the expression into a sum or a difference? Because then you can go back to the previous step and break up this one problem into many problems. So if you see a set of parentheses, can you FOIL or distribute it to turn it into a sum? If you see fractions, can you separate the fractions to turn it into a sum of fractions? If you see an exponent, can you rewrite that exponent using rational exponents? So if you have radicals, can you rewrite it as using rational exponents? The goal then is to make it look like x to a power. If it's a division of two polynomials, you might want to try using long division, because that will turn it into a sum or a difference. The other steps, P, F, and U, really you don't have yet. That'll happen later on in this class. Patterns is a certain thing called U substitution usually. Fitting or looking for certain forms, certain particular integrand forms have very specific techniques. One is, if you see trig functions, you're going to use trig identities quite a bit here. And you're going to rewrite it in such a way that it becomes a sum, if possible. And the very last one is U for oh dear God, this is going to be hard. And you don't really have anything there yet right now either. Most problems in your class, as of right now, can be handled way before this stage. but we will get a few in Calc 1 where we'll have to just try something. So let's go ahead and try this a couple times. Let's say I wanted to find what's the antiderivative of x times x minus 5. In the process, I would notice that this is a product with parentheses, so I'll go ahead and distribute that product. That way I could then find the antiderivative of each separate piece. But then I can take the constants out to get this new antiderivative. Notice the process of me multiplying it out allow me to distribute the integration through the sum and difference and through the constant multiples. I know how to find each of these antiderivatives. This would then be 1/3 x cubed. This would be minus 5, and the antiderivative of x would be x increased to the power multiplied by reciprocal to the power. And now that I've found an antiderivative, I can find all of them by putting on a constant. This is rewriting. This was integrating. The very last step is to go ahead and simplify. Don't leave it like this. You have 1/3 x cubed minus 5/2 x squared plus c. That's the answer. That is the general antiderivative for x times x plus 5. Now doing it again with this guy. Notice I can rewrite this one using the exponents. I write it as 4 times x to the negative 1/2. I can then take the constant out and take the antiderivative of x to the negative 1/2 dx. Then I have the 4. The integration of the dx are replaced with parentheses, and the inside I keep the x. I'm supposed to increase the power by 1, and then don't think of it as dividing by a half. Think of it as multiplying by reciprocal. So I multiply by the reciprocal of a half, that's 2. And then I can now finally put in the plus c. So this would then be 8, the square root of x plus c. This here was the rewriting. This is all the rewriting. This is the actual integration. This is the simplifying at the end. Let's do that some more. In this problem, I don't see parentheses, but I notice that I can rewrite the square root of x as x to the 1/2. That allows me then to find the product and rewrite it as x to 5/2 dx. And now that's the x to the n. So I have that rule. I take the power, I increase it by 1, I multiply by the reciprocal of the power, and I add c. That's that antiderivative. For the next one, notice I can write it as 2/9 times x to the negative 4 dx. I can then take the constant out and take the antiderivative of just x to the negative 4 dx. And I know how to find this antiderivative, x to the n. I just take the x, I increase the power by 1, and I multiply by the reciprocal of that power, and I add c. Now this time I'll have to rewrite that, make it look nice. That is the same as writing negative 2 over 27. This x to the negative 3, don't write negative exponents, just put it in the denominator, plus c. That's the answer. That's the derivative whose function, whose result is this. That's the function whose derivative is this expression. This next guy, notice you can write this one as x squared minus 3x plus 2 divided by x to the 1/2 dx. And then I can separate the fraction to write it as the integration of x to the 3/2 minus 3 times x to the 1/2 plus 2 times x to the negative 1/2 dx. Now I can find the antiderivative easy. I just take the x, I increase the power by 1, and I multiply by reciprocal of that power. Then I have minus 3. The antiderivative of x to the 1/2 is x. I increase the power. I multiply by the reciprocal of that power. And then I have plus 2. I take the x, I increase the power by 1, I multiply by the reciprocal of that power, and I add c. That's the antiderivative. All you have to do now is go back and just simplify that. Multiply those constants through. Don't leave it like that. Now sometimes though, the derivatives or antiderivatives are not quite so obvious. If you look at the antiderivative of secant squared of 4x, you would think, what function is there that when you take its derivative, you would get the secant squared of an angle. Well, that should be the tangent of the angle. But if I were to take the derivative of this expression, by the chain rule, whatever was inside doesn't change. So then this has to be the tangent of 4x. But if I take this guy's derivative, I don't get this. Because by the chain rule, I would have to take the derivative of this 4x eventually. Well, this is called correction by constants. The idea is to go through a small in-between step. To take the integration of the secant squared of 4x dx and to put a 4 here. When you do so, you're actually multiplying by 4. But that 4 can be brought in or out of the integral. Now, I can't just multiply by 4. That would then quadruple the answer. So I have to balance that 4. I'll balance it by multiplying by a fourth at the same time. That way, this will then be that answer. I just still have this 1/4 sitting at the end. So I wind up dividing by the constant that was missing. This derivative was 4. Notice I divided by that constant, plus c. This is overall correction by constants. But very, very, very few people actually write this stuff down. They usually just write down the answer. So doing it again, notice this is 2 times the integration of e to the 3x dx. So for this integral, you'd have 2 times the answer. But the antiderivative of e to the 3x, I'm looking for a function whose derivative is e to the 3x. That should be e to the 3x. But if I were to take this derivative, I would have to take the derivative of the exponent. That would be 3. I'd have a 3 here, but there wasn't a 3 there. That means that 3 must have canceled with something, so I will divide by the constant that was missing. This derivative should be e to the 3x. Notice the 2 is left behind because the 2 was brought out from the initial integrand. And now that I have the antiderivative, I can now put plus c. So the answer is 2/3 e to the 3x plus c. That's commonly called correction by constants, although some books don't even give it a name. Now do be careful though when you're finding your integrations. Always rewrite if possible. You want to fit your integrand to be one of the rules you have. So one of the rules is x to a power. So if you have an expression to a power, that's not x to a power. You really should rewrite that first. So you might be tempted to rewrite this as the integration of 3 times 2x to the negative 2 power dx. That's probably a bad idea. Don't do that at all. It's better instead to write this as the integration of 3 over, just distribute this product. You would get 4x squared dx. That would then be the integration of 3/4 and bring the x up instead. Notice how I write the integrals. I always write the constant and then times the function. This then lets me say 3/4. I need the antiderivative of x to the negative 2 dx. That will be 3/4. And the answer is take the x, increase the power, multiply by reciprocal of the power, and add your constant. Cleaning it up once, that'd be a negative 3/4, and the x goes in the denominator, plus c. That's the antiderivative of that function. For completion's sake, here are all the easy antiderivative rules that you get. Notice that every single one just comes from a derivative rule, where many times it's actually a composition of a function and kx. So then because of the composition kx, if you find the antiderivative, you have to compensate for the derivative of kx, which is k. To compensate for that multiplication of k, you divide by k. That's why pretty much all of these have a 1 over k in front of them. It's trying to take into account the correction of constants for you. I would strongly suggest that you memorize really all of these. So let's try some more of these. Let's find the antiderivative of the secant of x times the quantity tangent of x secant of x. Notice if you just multiply that out, it becomes a sum. That'd be the secant of x times tangent of x plus the secant squared of x dx. And I need a function whose derivative is secant of x tangent of x of an angle. That's just the secant of x. And then you need the antiderivative of the secant squared. I need a function whose derivative is secant squared. That's the tangent. And that's the answer, plus c. Now this one, though, requires more trickery. I don't have a antiderivative rule for cosine squared, because off the top of your head, you don't know a function whose derivative is cosine squared, do you? This is where you get into the forms part. It doesn't happen very often at this stage of integration. It's where you have a very specific function and you need a very specific technique. This is a trig function. I need to rewrite it. I want to rewrite it as a sum of things. So I recall that the cosine squared of twice some angle is 1/2 1 plus the cosine of twice that angle. This is called the power reduction identity. It's also given lots of other names: half angle identity, double angle formula. There's many ways it can come about. But we'll use it here to rewrite the integrand as 1/2 1 plus the cosine of just twice the angle, 6x dx. I can then distribute the multiplication, separate the integral. That will give you the integration of 1/2 dx plus the antiderivative of 1/2 the cosine of 6x dx. So the antiderivative of a constant is the constant times x. You then have plus 1/2. Now, to find the antiderivative of cosine of an angle, I need a function whose derivative is the cosine of the angle. That should be the sine of that angle. But if I were to do that, think about the derivative of the sine of 6x. But the chain rule, I would eventually need to take the derivative of 6x. I would have a multiplication of 6. But there's no multiplication of 6 in here. So I must have canceled with something. So out front, I'll divide by the constant that's missing. And I add c, my constant of integration. This is the answer. That's 1/2 x plus 1/12 the sine of 6x plus c. And that gives you the antiderivative of the cosine squared of 3x. If you see trig expressions in your integrand, don't despair. You just have to sometimes use your trig identities to turn that expression into a sum or difference of things that you can integrate. That also requires you then to know what you can integrate. So you have to memorize those formulas. Let's try some more. So if I wanted to find this antiderivative, it would then be 2 times the antiderivative of the sine of 3x dx minus 4 the antiderivative of e to the negative 3x dx. Do you see how every single integrand, every single integration begins with the integral symbol and it ends with a dx? That then would be equal to, you'd get 2. Now the antiderivative of sine, I need a function whose derivative is sine. But the derivative of cosine would be negative sine. I want sine. So then the derivative of negative cosine would then be negative, the derivative of cosine is negative sine, that's a negative, that'd be sine. So I should write down negative the cosine of the angle. But if I take this guy's derivative, I don't get the sine of 3x, because eventually I have to take care of the chain rule. The inside of this composition, its derivative is 3, but I don't see a 3 here. So that multiplication of 3 must have canceled. So there must have been a 1 over the constant I'm missing. Then you have minus 4. I need a derivative whose function, I need a function whose derivative would be e to the negative 3x. That should be e to the negative 3x. But if I take this guy's derivative by the chain rule, I have not yet taken into account the derivative of the exponent. I have not taken into account the product of negative 3. But there's no negative 3 there. So I'll compensate by dividing by the constant that's missing. That's the answer. Just go back and clean it up. That's negative 2/3 cosine of 3x plus 4/3 e to the negative 3x plus c. That's the answer. If you're never sure, if you're not sure you have the right answer, you can always check. You just check by taking this guy's derivative. If you take this derivative and you get the integrand, well then you're right. For the next one, to find the antiderivative of 1 over cosine squared, Notice that's a trig function, and the cosine square is in the denominator. So this time I don't use the trick I just showed you. Instead, I use a trig identity. I remember that 1 over cosine is secant. So this is really just the antiderivative of secant squared of x dx. And we know that antiderivative. We know the function whose derivative is secant squared. It's just the tangent of x. And we add on our constant integration. And that's how to do that problem. Now, you've seen there's many ways to find antiderivatives, and it's a bit of an art form. In order to be very good at it, you need to be able to do your derivatives correctly, because you're undoing that process. But let's get back to an application so you remember what this was sort of for, at least right now. A differential equation in x and y is just an equation that has x and y, and then the derivatives of y in terms of x, or the derivative of x in terms of y, depending upon what is independent and dependent. For example, if you have dy dx equals x squared minus 1, I'm trying to find all the functions so that its derivative will give you x squared minus 1. But if you look at the equation itself, all it really says is that if you take the derivative and you evaluate it at any point in the plane, this is the formula of how to find it. So then what I've done is I've taken this plane for you, and I've systematically broken it into a grid of points. And at every one of those points, I get a slope. And that gives me a tangent line. I then just drew for every single one of those points a very small baby version of the tangent line, so that all these little iron fillings were of the same length. This creates what's called a slope field. You use that to predict what the curve has to look like, because any curve you draw in this slope field can only be a solution to the differential equation if at all times the curve uses these things as guides or tangent lines. So for example, this curve here, that is not a solution. Whatever that curve is, it's not a solution to this particular differential equation, because at many places the corresponding tangent line is wrong. But you can use the lines to sort of guide you to see what the curve should look like. So it looks like one curve could be something like that, although up here it doesn't look quite right. But it looks pretty good. Now, if you have a differential equation, it doesn't give you one such function. There's going to be many functions. After all, look at this slope field. There's many curves that could go through this plane so that these little lines would all be tangent lines to the curves as I drew that curve. But there's only one such function that also has these conditions, that it goes to the point that when x is -1, y is 3. This point right here. And I can guess that the curve looks kind of like this if I drew it in, sort of like that. It's about what the solution looks like. So then if you look at the solutions of a differential equation, you don't tend to get one function. You get what's called a family of solutions. And they're all separated usually by, luckily for us, a constant. So let's solve our very first differential equation and not worry about nuances of what do we mean by the solution, what kind of domain would that solution have. Let's ignore those kind of details from now and focus more on how to do it. So there's some function whose derivative is 6x squared. Well, that means that this function f of x has to be a member of the family of the antiderivative of 6x squared dx, because this is all the functions whose derivatives is 6x squared. Now, but the antiderivative of 6x squared would be 2x cubed plus c. So this function must equal this expression for some choice of c. Now, this is an abusive notation because, strictly speaking, this is a family of functions, and a family of functions can never equal a single function. That's ridiculous. But this is something we often will write down in order to just get past it, to get to the answer. So all I know is that for some particular one constant, that f of x must be of this form. I just don't know what the constant is. So I do know, though, that f of 0 is -5. But I also know that f of 0 is 2 times 0 cubed plus c, that's c. Well, a function can't have two different values. So these two things imply then c has to be negative 5. Now that I know that, I can write down that the function whose derivative is 6x squared, and when you plug in 0 is negative 5, is 2x cubed minus 5. And as you'll learn later on in life, this has to be the only answer. This is the only such function where this is true. So as a fun application, let's go and verify something you probably have already learned in physics, which is how to determine the position of an object as it falls if you're given gravity and initial velocity. So let's assume that the acceleration, being the second derivative of position with regards to time, is negative 32 feet per second squared. Let's assume that the initial velocity, being the first derivative of position, is going to be v naught. And we'll say the initial position of the ball or object as it falls is given by the number s naught. So this then says here that the derivative of velocity with regards to time, that's the second derivative position, is negative 32. And the velocity at time 0 is v naught. So then v as a function of t must be a member of the family of antiderivatives of negative 32 dt. But we know this antiderivative, it's negative 32t plus our unknown constant. But because the condition, if I evaluate this when t is 0, I just get c. So c must be v naught. So the velocity at any time must be negative 32t plus v naught. But velocity is just the derivative of position with regards to time. So that is negative 32t plus v naught. And we know that the position at time 0 is given by s naught. Well then, that means that s must belong to the family of antiderivatives of negative 32t plus v naught dt. And that would be negative 16 t squared plus v naught t plus another unknown constant. Now see how I already have a c? You really shouldn't use another c, so I'll call this one c1, I'll call this guy c2. But we know though that when t is 0, the position is s naught. But if I evaluate this expression when t is 0, you just get c2. So c sub 2 and s naught are the same thing. So the position of the object at any time should be given by negative 16 t squared plus v naught t plus s naught. And that's a formula you often see in physics. And that gives you a very simple introduction to antiderivatives, how to evaluate some simple ones using some basic algebra tricks, and then an application looking at differential equations.